All right, so we are going to finish the textbook with a lecture on systems integration. Systems integration is downstream of the scope of this class, but it ties into considerations of how your design is going to impact the rest of your life cycle. So let's just talk about some things that you can like preemptively make your life easier downstream. For example, next semester is when you're going to actually build and integrate your system. So this is kind of like a taste into what next semester could look like. Let's just first define a few key concepts. So what is a system? A system is a little bit ambiguous, but in spacecraft, a system can mean different things depending on the scope of what you're talking about. At a minimum, a system is a set of things that you can define a boundary around. And so in this example, on the upper right corner, I have red boxes that bound different levels of systems. This biggest box is a boundary around the ISS with 4 different capsules included in what this definition of a system could be. So this is like an integrated ISS assembly as a system. But I also have these red rectangles around things that could still be considered systems, but at a smaller scale. So this Crew 2 Dragon from SpaceX, that in itself could be defined as your system of interest. In our class, we are going to be working more at the level of a single spacecraft like the Crew 2 Dragon or the Soyuz MS-18. And just as a little aside about these disparate capsule systems, each of these capsules deliver humans, supplies, science experiments, and outreach materials to the ISS. Okay, so that's a system. In this chapter, we are studying the phase in a spacecraft's life cycle where we integrate, test, and verify components, subsystems, and the entire spacecraft. Integration is the act of joining these disparate things together. Integration happens at the interfaces of the interfaces of the things. So in the case of the capsules and the ISS, the interfaces are the docking mechanisms that join just at the boundary of the red rectangle into the thing that is not in the red rectangle. And so we've been talking about interfaces a lot over the semester because when you're coming to actually integrate these components together, you need to make sure that the interfaces are consistent and compatible at that interface. In this case, the capsule's docking interface must be compatible with the ISS's docking interface. All right, so we were talking about this red rectangle. You could call this red rectangle an integrated system because we've integrated capsules onto the ISS. All right, verification is the act of checking if the system meets requirements, whether that's at a component level, subsystem, or spacecraft system level. We design tests to answer the question of, does my design fulfill the requirements? I think verification is more quantitative because typically we have data from testing or analysis that can numerically say if the requirement has been met or not. And then outside the scope of this chapter is something called validation. Validation is the act of checking if the customer needs have been satisfied, which happens before requirements and then after system integration during the operations phase. What we're trying to do in validation is verify that the intentions from the customer were properly translated into requirements, and then if the operations fulfill those stakeholders' desires. Okay, let's move on to testing and verification methods. There are 2 types of verification methods, static and dynamic, and I borrowed these terms from software engineering. And you can distinguish between these 2 by whether you are poking and prodding into your system or not. So static verification is where you're not poking into the system, you're more so holding it afar, inspecting the system for flaws, or reasoning through the logic of the design. So an example of reasoning through the logic is if you were to sit down with an expert and then you were to discuss the thought process out with the expert, then the expert would evaluate if the design sufficiently meets those requirements. I've kind of been informally doing that with you all throughout the class, well, actually formally. And so that kind of verification is static verification. That's going to be different than dynamic verification, which is more invasive. That's where we craft verification tests that interact with the system. That could be through physical testing, simulation runs where you're exercising your software, or design analysis when you're loading components. Okay. And something that's really important is on the right, that is an example of documentation as offered by NASA. Documentation is absolutely key for testing or verification. As the old adage goes, Pixar didn't happen. The same can be said about spacecraft, documentation, or I don't believe you. So let's walk through this sample verification test report from NASA that can act as a cover page for your verification test report. All right, so in this form, you want to be specific about what page it is. It's going to be a cover page, so let's say it's like one of many. And then you want to specify what project you're working on, what the test item is, so like a word descriptor of it, the manufacturer, and the serial number. We really want to be as specific as like looking at the barcode and the serial number on your component. And if you built that component, you want to label that component with like a serial number. That is the level of like specificity that we need to impose on the engineering design process. Okay, and then outside of that, we need to define the level of assembly. So here, NASA's level of assembly, it's a little bit more rigorous than what we really need to get into for our more simple systems, but they have like subassembly, unit, section, subsystem or instrument, module. For hardware, remember in the chapter, I'm going to be going over this later, but there are different versions of the hardware. I just talk about engineering units or flight units, but here they have other things like a prototype, a flight spare, and then the type of test. Are we doing an initial test of this system or are we retesting? And then the suite of tests that you can perform down here. So there are some pretty generic ones that most components are going to have to go through. So under structural tests, it may include structural loads, vibration, acoustics, shock, so on. For electromagnetic compatibility, there are different types of radiation. For electrical performance, there are these different subtests. For thermal, there are these different subtests. And for optical, make your own test. But even if you don't check off any of these particular categories of test, you can create your own test procedure. Down here, it's kind of like in between the lines, small font, but you really want to write your own procedure for every test that you do. So this is answering one of the questions about how comprehensive should the test be? You need to be as specific as, you need to be very comprehensive. There should be like a step-by-step IKEA procedure where that goes with every single verification test. Literally, which size screw, like an M20 or an M5 or like a 420 screw goes into this bolt hole within the structure. And it needs to be fastened to this amount of torque with this torque wrench. It could be as specific as like, which commands do you enter into your computer? And so the labs that we did, for example, you were copy pasting down to the character what things you need to be entered into your command line to run a certain function. And then electrically, that could mean like, which pins do the connectors interface with? So on a CSKB connector, which is this like 2 by whatever or 4 by whatever amount of pins, it is the second row, fourth pin that you need to plug this cable into. Like these tests are super, super specific so that anyone can run the test and it would be foolproof. All right, so think about this when you're filling in your verification methods. We eventually need to get here before we fly your satellites. Okay, so examples With the Artemis CubeSat kit, I've designed all of the labs to act as some kind of verification method for the designs. For the Artemis CubeSat kit, each subsystem had a static verification method tied to it. That should be software tests. But anyway, for structures, remember we did a mass budget and we did a finite element analysis. For the power subsystem, we did a power budget and profile. For communications, we made a link budget to verify that your link closed. For the thermal subsystem, we didn't quite close the loop here, but we were working towards a verification of your thermal budget and profile. For attitude, determination, control, and sensing, we generated a pointing budget, and then command and data handling, we tried to do the Ephraim Hello World. Okay, and then for next semester, what we're thinking about doing for the physical labs when you're designing building is to have verification methods like so. For your payload, this could mean capturing an image and then analyzing the resolution of that image. For structures, it could mean actually physically loading the primary structure and then just inspecting that the structure survived and didn't deform. For power, it could be measuring the voltage from a solar panel. From communications, it could be transmitting a command from a physical ground station and verifying that your signal was received through your antenna and then your radio. For thermal, it could be putting your spacecraft into a thermal vacuum chamber and then measuring the temperature of components throughout time. For attitude, determination, control, and sensing, that could be turning your torque coils on and then measuring the resultant magnetic field. And then command and data handling, that could be collecting actual sensor data from your sensors on board. So these are all examples of static and dynamic verification and things that we all did or will do next semester. All right, let's talk about the general process of system integration. I'm kind of glazing over the design to then integration process. So if we were to look at this verification and validation model, we are focusing on this part of the project definition. But before we get to system integration, we have to do implementation. So what does that entail? The system implementation part is where you either buy, build, or reuse components that compose the subsystems and the system. Having been through the entire design process, every phase of the life cycle either influences or is influenced by other phases of the life cycle. So it's good to know the context for the entire cycle whenever you're doing any one phase. The way that we source our design solution heavily impacts the system integration and testing phase in the schedule and ease of use. So I am going to talk about curiosity and perseverance, but as a real life example of reuse on campus is that the high-tie satellite had a bunch of spare components that they gifted to VIACES. So that is a prime example of reuse. Another example of reuse is that I'm giving you Artemis CubeSat kits, and Genesis is adopting a lot of those components and reusing those designs for your design. So reuse, let's take Curiosity and Perseverance as an example. NASA holds these two rovers up as a shining example of reuse. And their intention was that NASA was trying to save money and schedule by reusing most of Curiosity's bus, but expanding the science capabilities into the Perseverance mission. From Robert Wessel, which is where I got this picture and his words, he said, "Perseverance is mechanically an upgraded Curiosity. A number of changes based on experience have been made, like stronger wheels, and to increase capability, like a bigger robotic arm, but they're very similar vehicles. The flight hardware, landing technique, and all that are basically the same. The science package is quite different though, and its mission is somewhat different, amongst other things, more directly looking for signs of life on Mars." So a little bit more about Perseverance. Perseverance is doing really well on Mars right now. because to answer one of the questions about like how can you make sure that these components are functional, well, you test them. You test these leftover components from Curiosity before you send it up into space. And so shout out to Genesis and Vices, like you really should independently functionally test the components that you are gifted, because you just don't know you just don't know until you actually do the test. Granted, there are pros and cons to reusing. For this particular mission of translating to Perseverance, the mission was a better bang for NASA's buck and had a shorter schedule than a new design, but reusing the components from Curiosity's time meant that components were like a decade old by the time they were integrated into Perseverance. But then the flip side to that is because those components had heritage, there was less risk associated with the design and more experience with testing, even though the functional performance is, a decade old. Imagine using a decade-old computer, for example. Not as functional, but you know what the problems are going to be, and you can look up the problems on Stack Exchange, Yeah. Okay. Okay. Let us talk about the system integration phase and what that more specifically looks like. If we were to zoom in on the system, the integration test and verification, and then the system verification and validation phase, it might break down into more discrete actions that look like this. So here's a flow diagram of the different tests that these phases may include. On the left, this is the software trajectory. So a unit test refers to testing a single script, making sure that with this range of inputs that you get these expected outputs. And so once you test each individual script, then you can integrate those scripts together and do a module test where you're really testing the, accumulated manipulation of a data signal going from the input script to some eventually nested output script. The same analogy can be made on the right for hardware components. You want to check out the health and functionality of individual components. So this could be like a star tracker or an IMU, making sure that when you point it at the night sky, that it outputs a quaternion. Or if you rotate the IMU, that you're getting reasonable angular rates. And then let's say you integrate those two things together. The star tracker and the IMU don't necessarily form the entire subsystem. Maybe there are sensors and sun sensors and stuff involved. So the module test is not quite the subsystem, but is the joining of individual components. And when you say join the star tracker and the IMU together, the added functionality that you're testing for is potentially an attitude estimator. Okay, and then once you're done doing these more low-level tests, you can integrate these components in the software into a subsystem, and then you can test that subsystem. Once you integrate subsystems together, then you've got an entire spacecraft that's integrated, and then you can do spacecraft-level tests. Yeah, and then so that is an example of what could go into this process of integration, testing, and verification. All right, here's another flow block diagram from Lisa Bagel about the assembly, integration, and testing phase. I just want to give another example where there are more specific callouts to certain subsystems. So maybe you can use this as a roadmap for how your process may go for system integration. Let's kind of just walk through it. So let's say you start out with your bus structure, and then you start integrating internal components that live on the inside of the bus. At that point, you start to do physical inspections to see that the integration was, structurally strong. Then you do some bus functional tests. This could lead to folding in the panels and securing the primary structure, and then you install external components like solar panels. Then you do more bus functional tests. At that point, maybe you're ready to install your payload. So before then, you assemble your payload, you then install it, do a functional test, do some payload calibration and alignments. Then you measure the mass properties of your bus assembly because your spacecraft is complete at that point. Then you do a vibe test. You do some more functional tests to make sure that the vibration test didn't break anything. After your functional tests, maybe you deploy your solar panels and you illuminate them and measure the voltage that comes out. At that point, you can integrate your mission flight software into the spacecraft and then exercise the spacecraft through some mission scenarios. Then you can test some off-nominal scenarios. And then you can maybe mate that spacecraft into the deployer or the launch provider interface. And then you can pack and ship that spacecraft to the launch site. Okay. All right. So I want to talk about typical requirements and design considerations. We are getting to the point where we were high level. Remember at the beginning of the semester, we were science and payload and then system level. And then we went into each subsystem down to like the components, but now we're coming back up. So think about system integration and how that could inspire some requirements at the subsystem or system level. If not requirements, there are some considerations that you have to incorporate into your design. Some of them are manufacturability for the purpose of fabrication, technical interfaces, modularity, and ease of access. So to give examples of how these considerations could impact your design, let's look at this example where, let's say you designed a custom mount component for a part in your spacecraft. If you were to upload that design onto ProtoCase and then they generate a quote, what you can do is iterate that design by modifying the radius of corners of different bevels to see if you can get that cost down. I think this could be kind of important for y'all with a smaller budget. Maybe this doesn't matter as much for really big projects, but it can make quite a difference of like a couple $100 if you just change very minor things about your structure. And this could also be the case for printed circuit boards. If you're an electrical engineer and the things that really drive up the cost of printed circuit boards are the number of layers in your printed circuit board. You have to like understand the vendor's calculation into this, like they have to customize their equipment to fabricate the thing that you're interested in. And if you understand their process a little bit about how they manufacture things, it could save you a lot of money. Okay, for technical interfaces, I think I've really stressed this throughout the entire semester. But you gotta make sure that your component on this side matches your component's interface on the other side. Because if they don't, and you are at the point where you bought the component and you're ready to integrate, they're either going to short circuit each other or not talk to each other. But either way, you've like wasted money and time. So please, 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 like in your system diagrams, I've stressed this so much about interfaces. It could be a huge headache if you don't pay attention to interfaces. That's where designs fail the most, at interfaces. All right. Here's a picture, for example, of a launch provider's interface for satellites. This is a ring, and so the interface control documents for these different launch providers include mechanical interfaces like this, where it's down to the dimensions of like what you should be mounting to. And then there are also like electrical interface documents if you need power from the launch provider. Modularity and ease of use. these are nice things to have, but they could be also requirements. If you want to functionally check out a component that is embedded within your satellite pretty far in, if you didn't, let's say there's some oversight and you integrated a bunch of components around the subject that you want to test and you can't access it, then you literally cannot verify the requirement because you didn't think about when you were integrating things and whether it would be accessible during that phase of integration. So definitely think about ease of use for your future self. Okay. And then there was a question about, is modularity or ease of use more preferred? So I think that they're both nice to have in different situations. The modularity is more so about if a component or subsystem breaks, how quickly can you shove in a spare component? And then the ease of access is more so for testing. I think they're both important. How do factors such as material selection, process complexity, and vendor capabilities impact not just cost and schedule, but the overall success of a project? So I think this points out to the manufacturability. The material cost affects budget, but it also affects your structural analysis. The process complexity, like how many holes or how like geometrically complex do you have to mill out for this certain part, that has to do with schedule and cost. But also, I guess, your structural analysis. And then your vendor capabilities, that is a good question. So we've had bad experience with a company called Exometry where their capabilities were not very high. They were cheap, but they were not as trustworthy. And so we got our parts in, they were the wrong dimension. And that was such a pain in the butt, schedule-wise and budget-wise, because they didn't refund us the cost. We had to just buy another set of the right dimension. So vendor capabilities, unfortunately, that's like a soft programmatic skill that you have to learn. It's kind of a problem in the space industry because these parts are so custom and people don't really talk to each other about like which vendors are good or not. You can kind of get bit in the butt if you don't have experience and then just go for a random company. Yeah. This is something that we want to fix as a community and have a database of like trustworthiness for companies. Okay. If the functionality of the entire subsystem is on a single board, if one element stops working and needs to be replaced, would the entire board need to be replaced? If so, you would be trading modularity for cost, right? Yeah, so this question was about modularity and like if I could use these Artemis boards as an example, if say one of the resistors stops working, we do have the capabilities in-house to switch out that resistor and then solder on another. If it's a more complex component like a processor with really small soldering pads that is hard to replace, you'd have to replace that whole board. Let's see, with the entire board, you'd be trading modularity for cost. I think, yeah, the pros and cons of modularity are that it is a little artificial to put all of your subsystem in a single board. So there's like design time and cost in trying to design in a modular way. But if we were to then talk about the implications when you're actually designing and testing, if you order multiple boards, as you should, then you can just swap it in and out. And so you save time during the testing process. There are trade-offs. Who should be in charge of the interface in role distribution? I would say that, let's say it's an interface between the electrical power system and the command and data handling system. The interface should belong to both systems, both subsystems. The electrical power system should be responsible for the harness that's coming in on the left, and the command and data handling, if they're responsible for the board on the right, they should be responsible for receiving that connector. So those two people are both responsible. If the interface is bad, both those people should be criticized. Okay, and then what are the Artemis kits being reused from? I was mentioning that the Artemis kits are being reused because year to year, we're using the same kits for our students. So like the kits that you touch may have been touched by students from 2022, for example. But yeah, okay. This is the last section. So it's about general setup and design drivers. System integration and testing is the most expensive part of a life cycle. It is best practices include having spare parts. So on the left, what I'm showing is an engineering design unit that the Artemis CubeSat team set aside so that we could really exercise the components in this unit. But then when we were mass manufacturing a bunch of kits that we were going to give out to other people, we barely touched them. We just very lightly exercise them by checking out their help and then doing very minimal functional testing, because the components are identical, but we want to make sure that there is minimal wear and tear on the actual flight unit that we're giving out. So the difference here is that the engineering design unit, we, for example, will do day in the life tests where we power it on for like 24/7, and we just have it run computation for the scripts and take in sensor measurements throughout that entire period. As you know, your phones, your laptops, they degrade their performance over time. And we want to prevent that for the flight units, which is why we set a unit aside to do that kind of rigorous testing. Once the engineering design units are decommissioned and the flight units deployed, does the certification from the test stay with the hardware and can be used to reduce costs on future developments? So yes, I think that certifications can stay with the hardware. Oh, another thing about engineering design units is that once the flight unit is operational, typically people don't decommission the engineering design units. They will actually mimic what the spacecraft is doing in space on the engineering design unit so that they have some kind of parallel, I guess, parallel track or life of the spacecraft. What's hard about these flight units is that you don't get to observe them very frequently if they don't talk to ground frequently. So what you can do is simulate very realistic conditions on the engineering design unit on ground and then probe it much more often than you can probe a flight unit. So that's like another cool use for engineering design units. Okay, let's talk about systems level tests. We're going to go through your requirements and fill out the verification tests. I realize that I asked you to do this without really knowing what the full scope of tests could be. So here is, I guess, a library of what you could update the tests to be. There are functional tests, which are going to be specific to the functionality of your component. But then there are more environmental tests like shock tests, acoustic tests, and vibration tests. And then there is a test that is specific to electromagnetic compatibility. It is to make sure that there's not much interference between your sensitive components and then the environment that it's operating in. Okay, and then what does environment verification refer to? Does it mean considerations for how the system will behave under expected environments? Mostly, when it comes to environmental tests, it is about survival. It's not really about functionality. These environmental tests are transient. They're trying to simulate the launch vehicle conditions. And so your spacecraft is not going to be operating during launch. It's mostly going to endure and survive launch. So that's what these tests are supposed to do. bottom. Okay. Let's talk about ground support equipment you may need for system integration and testing. On the right here is a picture from ISIS where they can sell you for a pretty penny an umbilical cord so that you can integrate your spacecraft, pack it in this deployer, but then you can still do testing through this cord. So this cord will offer power and data. This is particularly good if you're ahead of schedule, you've integrated your spacecraft, or like you've built in time specifically to test your integrated spacecraft while it's in its deployer. Some other ground support equipment that are specific to other subsystems could be for the telemetry and control. It's your comm system. It could be a ground radio. It could be fiber optic cabling, a workstation. For power, it could be a solar array simulator. We have used, for example, testing our solar panels, a lamp that like emulates the spectra of the sun. For mechanical, your ground support equipment could be an integration stand, a torque screwdriver, different hand tools, anything that requires you to integrate and test your spacecraft. And there's going to be a lot more of that equipment than the actual spacecraft itself. And then here I have a picture of a GPS simulator. So here's like a more precise and accurate GPS receiver to verify what your spacecraft GPS might be reading. So that's also included in ground support equipment. All right. Not only do you need ground support equipment, you also need ground testing software. So I'm going to be talking about these different software architectures in increasing levels of relevance to spaceflight environments. So within HSFL, there is a software environment called Cosmos. And Cosmos has the ability to not only be flight software, but also to be a simulation environment to test flight software. And so if we were to take attitude determination control and sensing as the case study, here, the simulation would spoof or kind of like generate fake measurements of, say, GPS, the gyroscope, and the sun sensor and feed it into the flight software so that we can test the functionality and capabilities of the flight software. So you would typically, this is called processor in the loop, and you would typically do this in the like module testing phase of integration and testing. This hardware in the loop is where instead of relying on the simulation to spoof a bunch of these measurements, you're translating much more of those measurements into the physical realm. So then we'll have, say, environment simulators where you're actually physically emulating what the spacecraft will be experiencing. This could be like on an air bearing, in a Helmholtz cage, which spoofs magnetic field, a floodlight, which could be the sun. And so these physical simulators then feed into, they actually physically emulate physics on the satellite, and then your sensors will actually generate real measurements, but on ground, and then feed that into flight software. This is called hardware in the loop. And so you can see we're getting increasingly realistic to what the spacecraft will actually experience. And so that physical test bed looks something like this. This is downstairs in the basement. All right, to answer a couple of questions, can you further explain the collaboration dynamics between the command and data handling specialist and the integration testing engineer? So the command and data handling specialist is responsible for the flight software, and then the integration and testing engineers are responsible for everything that's not that flight software. And so the CDH technical specialist will have to communicate to the integration and test engineers, what is the interface here? Like what kind of measurements do I need my simulation to be generating? Or even here, if I'm in hardware in the loop, um, the ADCS specialist would actually start to step in here for the GPS, IMU, and sun sensor, but they would be talking to the integration and test engineers about, oh, I would really like the air bearing to be rotating at this speed, or I want the Helmholtz cage to be emulating the magnetic field for this orbit. Okay, cool. How accurate are these simulations and how often are they used? This test bed over here was like $500,000, and not every university has the capability to buy test beds that are this rigorous. So these simulations are very accurate, or they can be very accurate if you design the experiment to like the maximum capabilities of the test bed, but they may not be used often due to budget because you can't buy a test bed that is this capable, or because of schedule, because you just don't have enough time in the satellite integration process. And that's something that, the Hawaii Spaceflight Lab has experienced where the attitude, determination, control, and sensing subsystem typically is left until the end. And so then the schedule interferes with launch. So this usually doesn't get as much time as you would. Yeah. All right. Another study of increasing relevance of functional testing. Remember, we were trying to do this thermal modeling, finite element analysis. So that is one level of accuracy and precision. But if you were to increase the relevance and accuracy of your thermal control system, you may test it in a thermal vacuum chamber. There's a question here about how accurate are the thermal tests utilizing a hot plate and a cold shroud. So in this thermal vacuum chamber, there's this ring that's not really touching the outer vessel. This is a black shroud. And if we were to remember concepts from the thermal chapter, we would remember black body radiation. And so this black shroud is trying to emulate the black body of the universe. There's this plate that the spacecraft is mounted on, and typically you can heat up this plate. And then on this black shroud, you also have loops of liquid nitrogen going through to make it really cold. So how accurate is this? The hot plate is not necessarily that accurate because it's transferring heat through conduction, but I've also seen thermal vacuum chambers where they put a light, so like a radiation source within the thermal vacuum chamber to emulate the sun. Did you want to ask a question? No, okay. And then the black shroud is supposed to emulate the black body radiation of like the far, far away universe, right? Infinitely far. But it is physically a certain distance away. So while it's not the most accurate to space, it is still going to be more accurate than a like finite element model, because you're actually exercising the physical equipment, which may have differences than the assumptions that you made in your software model. Okay, 2 more slides. So we were talking about how this is the most expensive. It's because we want to get physically more and more realistic of space environment conditions. Here we see a blueprint of the Malaysian Space Agency's facilities. To do all these tests, you need to have very specialized facilities. And so, for example, the electromagnetic capability test chamber may look like this. The mass properties measurement may have this kind of shake table that looks like this, or sorry, I'm not sure if this is exactly a shake table. This might be a more like a dynamometer table. The vibration or shake table can be in this room. The alignment measurement room could look like this with all that equipment. The optic calibration might look like this with like collimator or something. The acoustic test room looks like this, and the thermal vacuum chamber is in this other room. So you can see a lot of space necessary, a lot of money for equipment, especially specialized equipment, is required. So the question then is, when these tests are not possible with the spacecraft in its entirety, either due to cost or time, are individual parts or clusters of parts tested, or are similar tests used that can accommodate certain constraints? Yeah, so like if you don't have facilities like this, you can stop at less relevant environments. You can stop at a finite element model, or you could stop at like, instead of having all of this hardware, you could stop at a processor in the loop. There are always trade-offs. So if you don't have the money or the time for these more expensive but more accurate things, then you just accept that your tests are going to be less accurate and that the way you behave in space may not be as representative of what you saw in your testing. That's okay. If you have a riskier mission, that may fulfill the requirements. All right. Sorry, 2 more slides. Here are different types of qualification and acceptance tests. So what I really love about these tables are that there are inevitably going to be things that go wrong. And so this will tell you the way you can detect something going wrong with a certain test. So if you were to detect a like adjacent circuit board contact, the test that would illuminate problems like that would be a vibration or acoustic test, a shock test, or an EME test. And there are going to be different tests that reveal different flaws. Leaky gaskets, for example, are going to be through a leakage or an EME test. This table could also tell you about which tests will reveal the most flaws. And so it looks like here that the vibration test, the EME test, and then the acceleration test, if you were to only do a limited number of tests, those would reveal the most flaws. Okay, and then same about these acceptance tests. Okay, and then there was a question, since requirements seem so exhaustive, are these just errors in execution, like errors in wiring, or is something not properly installed, that sort of thing? There are a ton of reasons for these errors. It could be an error in design, an error in manufacturing, an error in integration. But then these tests, they will identify the error and they don't necessarily identify the root cause of the error. But at least you know what the error is, and then you can rectify it after you identify it.
I mean, it seems like those higher level errors
Yeah.
should have been caught already earlier, since you have all these requirements that you tested at all stages.
Oh, I see what you mean.
Yeah.
Maybe, maybe not. Your verification tests may not be comprehensive of all the problems that you may experience. It may be that only through integration are you going to notice interface errors, for example.
Okay, the design is not good.
It could be design or manufacturing or integration. Which is why you want to test throughout the entire life cycle, like, right? You want to do testing not only at these individual components, but then at these after you install them, you know? Like you want to be testing at each level.
Why they need a really comprehensive plan so that you don't go at the end and the problem was from the top. That would be really hard to trace.
Yes, that is a great point. The reason why we do unit and subsystem testing is so that we can isolate errors. Because if you were to wait to do testing until the very end, this one test, something can go wrong, but you won't be able to know whether it was a mounting problem or a defective part problem. You would be able to distinguish and isolate the problem if you were to say if you were to test the individual component and just figure out if it was healthy, then it's not a defective board. It's probably an integration problem due to the mounting being broken or loose, right? So the more tests you do, the more you can isolate and like cross off things that it couldn't be. Yeah. Fabulous. Good line of questioning. Okay. Last slide. Fault testing. Faults are things that you don't want. Other ways of saying fault are anomalies, operational anomalies. They're things that you didn't anticipate. Before you get into space, you can test for faults by willingly putting your spacecraft in situations that are nonsensical and then seeing if the flight software or the components detect it and then protect against it. So for example, here is a software block diagram where there's this command and data handling system. Okay, let's say you are the ground system and you're transmitting to the spacecraft, and then it's broken up to these different subsystems. You can transmit, are like weird commands or spoof weird environment references, and then see if the fault is detected. Sorry, the resolution's bad. Whether the attitude control system is going to detect and then protect against that fault. So you want to do some level of this. The level of fault testing scales with the budget and the schedule of a project. You all might not get to it, but if it were a flagship mission that is like billions of dollars in budget, they do dedicate a ton of money towards fault testing because it's like a one-shot success project. It's so critical that things just go right the first time around that you want to test as many scenarios as possible to make sure you get it right the first time. Okay, last question. What systems are created in a satellite to correct potential power problems? So for example, this line is the power system. What systems? So to protect power systems, there's a fault detection and fault protection. So an example of this is if you were to get a nonsensical value for your battery state of charge, that could be due to a bit flip. So this fault detection would be like, hey, that is a weird measurement. And then it sends that flag to fault protection, and then fault protection is like, I think I'm going to restart the onboard computer, or I'm going to not accept this measurement and just wait for the next measurement. So that could be like one method of protection against, let's say if you get a weird state of charge from your battery and it could trigger the battery totally discharging or entering an unsafe mode. So yeah, you want to detect it, and then you want to protect against it. Hope that was clear. Okay, so that is the end of my lecture. Does anyone have any questions? I can also